चलिए स्टार्ट करते हैं।
Hello friends, this is Mr. Sarvesh Varzurkar. We are here for the session organized by Ballarpur Institute of Technology under AICT sponsored Prerna scheme for SC and SC students. Uh, in the subject computer science, we are now going to deal with the upcoming 4 lectures will be for this algorithms. In that algorithms, the topic which we are going to cover for today's class is like asymptotic notations and worst case time and space complexity for every algorithms. See, the first of all, what is algorithm? The question arises, what is algorithm? Algorithm is a finite set of precise instructions. It is a finite set of precise instructions for performing a computation or for solving a problem. For any normal problem, you required a step-by-step executions or a step-by-step set of instruction for performing any type of computation to solve any problem in the world. It can relate with your our normal life as well. This is rather a vague definition, as you know that this is a vague definition, but you will get to know more precise and mathematically when useful definition when you attend our next slide. But this one is not good enough for now. I can say there are certain properties of algorithm. If you follow all the properties, your algorithm will be in a very perfect manner. It runs in a very perfect manner. First is input from a specified set, output from a specified set, definiteness of every step in the computation, correctness of every possible input, finiteness of every number of calculation steps, like how many number of steps required, how many number of calculations are required. According to the correctness, whatever the correct output is required, again it will be there with the help of correctness of output of for every possible input. Next one is definiteness, as we have already discussed, and last one is effectiveness. Of course, effectiveness is very important. Unless and until if you want to prove your algorithm is very effective, you have to follow all these particular properties. In terms of a normal definition, an algorithm is a set of operations to solve any problem performing calculation. It may be of data processing, it may be automated reasoning or any task. An algorithm is an efficient method that can express is a very efficient method that can express within finite amount of time and space. Time and space are the two different parameters on which the effectiveness or effectivity of the algorithm is being calculated. An algorithm is the best way to represent the solution of a particular problem in very simple and efficient way. There are various examples that we are going to see it right now. Yes. If we have any algorithm for a specific problem, then we can implement it in any programming language. If you have the pseudo code, you can you can if you have the pseudo code, if you have the flow chart, if you have the syntax, you can apply it in any different type of programming language, meaning that algorithm is independent, meaning that algorithm is independent, and we can simply say that for any different programming languages, the algorithm for any different operation will be same. If it's up to you, you can perform it in any specific language. It may be say C, it may be say Pascal, it may be say Python, it may be any different language. We will use the pseudocode to specify the algorithm, which slightly reminds us the basics and Pascal. For example, an algorithm that finds the maximum element in a finite sequence, procedure is same. Like the steps are very same. Like procedure maximum from A1 to up to AN, whatever the integers, and max is whatever the maximum value that should be A1 for I is equal to 2 to N. And if max A1, if the value is maximum, which is less than or equal to A1, then max is equal to A1. That's it. All the remaining values are less than A1. That's it. It directly means that your final value is max. That max is the largest element, I can say. This is the algorithm. This is the algorithm. It may be applicable in Java, it may be applicable in C. The same algorithm may be applicable in Pascal, in C, C++, Java, Python, any different languages. Again, certain example, we can go with the linear search algorithm. That is an algorithm which is linearly searches for a sequence for a particular element. Where if you want to search a sequence for a particular element, this will be the syntax, or this will be the steps, or this will be the algorithm, I can say. Where procedure linear search, x, you can initiate this integer a1 to up to an, and all are integer if I is equal to 1, while I is less than n and x is not equal to I is equal to I plus 1. If I is less than n, then location is equal to I, whatever that location, else location is equal to 0. It means if the normal condition, if I is less than or equal to n, n is nothing but the integer, and then location is equal to I. That means ultimately you will get the sequence. Else location is equal to 0. Location is the subscript. That will be the answer. The line which is mentioned in that green color is the answer, where the location is the subscript of the term that equals to x, or is 0 if x is not found. If in terms of in terms in a sequence or order in a binary search algorithm is more efficient than linear search. There are two different types of searching algorithms. One is linear search and another one is binary search. The second one is the binary search. We will see it later on. The binary search algorithm iteratively restricts the relevant search interval until it closes in on the position of the element that to be located. Whereas uh, linear search can go in a very sequential manner. There are various important aspect of algorithm design that includes creating an efficient algorithm to solve a problem in an efficient way by using, say, minimum time and space. This is the normal example of our searching in binary, as we have just now discussed. Look, binary search from the given list of elements, from the given array, I can say, from the given array, if we are going to search it for the letter J, how can it possible? The binary search algorithm says that from the given list of element, you have to first choose the center element. You have to divide the whole list of elements or the array, complete array, into two different parts by simply looking at the center element. For example, if I can, if all the elements are in alphabetical order, and we have finding that all are in alphabetical order, look at this: a c d f g h j l m o p r s u v x and z. In that case, the letter which we are searching for should be in the first half or in the first interval. The whole list is divided into two different parts, that is two intervals, interval 1 and say interval 2. If we are searching for j, we will know there is no any need to search in the second interval. Why? Because j is less than m. So ultimately we have to our targeted element will be before the m, or it should be in the search interval first. Again the same part. Again the same part. If in that search interval first we again divided it into two different parts, again we need to find it out the center element, and from that center element we are going to compare our element, and then it will be again subdivided into next sub part. Again we need to do the center element and the search interval may be there. Ultimately we may definitely found our element for which we are searching it for. Same thing if our element is, for example, say u or v, it is in the second interval on the first line. In that case we again need to repeat it, we again need to perform the same operation again and again unless and until our element get found. This is the procedure for binary search x as a integers, like a1 a2 up to an. I is equal to 1, j is equal to n, where I is the left end point of the search interval and j is the right end point of the search interval. While I is less than j, it means that we have to start it from there. Ultimately, m is equal to mod of I plus j divided by 2, where x is greater than, if x is greater than am, then I is equal to m plus 1, else j is equal to m. It means directly means that if the finding location for which we are searching for is greater than the value, it should be it should be 0, otherwise it is equal to that particular value, that is j is equal to m, and our element may get found over there. Location is the subscript of the term that equals to x or is 0 if x is not found. Next is complexity. In terms of complexity, we will first of all go into the algorithm first, and then we'll then we'll enter into the various problem. For example, to solve any different problem, yes, to solve any different problem, different approaches can be followed. Some of them can be efficient with respect to the time consumption, whereas other approaches may be memory efficient. The time and memory are nothing but the complexity. However, one has to keep in mind that both time consumption and memory usage cannot be optimized simultaneously. Of course, if we are working for algorithm, if we are thinking it like if in an efficient way, so we'll definitely work it in that efficient manner, so that we have to create the algorithm in that efficient manner, so that it it will be very much efficient in terms of time, along with in terms of space as well. So one has to keep in mind that both time consumption and memory usage cannot be optimized simultaneously. If we require any algorithm to run at a lesser time, we have to invest more memory. If we require an algorithm to run with lesser memory, maybe it required more time. I can say that time and memory are inversely proportional to each other. The one true or false type of question was there in gate in the year 2000, around 11 12, in that area, in that year. uh, Time complexity is inversely proportional to space complexity, that means memory complexity. The answer is true itself. Two options were there, the true or false. You need to answer true if it is there. Okay. Problem definition, problem development steps. There are various steps that may be required at the time of computational problems, like problem definition, development of a model, specification of an algorithm. We can also say that design of an algorithm, checking the correctness of an algorithm, and at last analysis, implementation, and then testing, and lastly the documentation will be there. Accordingly, various characteristics if we working out, like algorithms must have a unique name. You may not copy the same name for your algorithm. It should be of unique. Algorithm should have explicitly defined set of inputs and outputs. Algorithm are well ordered within the unambiguous operations. Along with that, algorithm have a halt in a finite amount of time, whereas algorithm should not run for infinity. That is, an algorithm must end at some point. It should have certain finiteness as well. In general, we are not that much interested in time and space complexity for small inputs, but whenever the inputs or whenever the size of the inputs are high, ultimately the time and space complexity matters. While the difference in time complexity between linear and binary search is meaningless for the sequence with n means the number or the integer is equal to 10, it is it is negligible, or it is gigantic for n is equal to 2 to the power 30. If in that case your time and space complexity really matters a lot. How? We'll see. For example, let us assume the two algorithms, say A and B, that can be solved in a same class of problem. The time complexity for A is required around 5000, and the B and the one for B is around 1.1 to the power n for an input with n elements. For n is equal to 10, A requires, for example, say 50,000 steps, but B only required 3 steps. So B seems to be superior to A. Ultimately, for n is equal to 1000, however, A requires around 50 lakh steps. while B requires 2.5 multiplied by 10 to the power 41 steps. It's a huge amount. There may be a lot of complexity occurs in terms of time, in terms of space as well. This means that B cannot be used for large input while algorithm A is still feasible. So what is important is the growth of the complexity function. What is important is the growth of the complexity function, and the growth of the time and space complexity with increasing input size n is a suitable measure for the comparison of any algorithm. Comparison time complexity of algorithms A and B. For example, say algorithm A and algorithm B along with the input size. I can have the complete table with me. N size, algorithm A requires 5000 n, algorithm B requires 1.1 multiplied by 1 to the power n. For input size 10, A requires 50,000, B requires 300, A requires around 5 lakh, and B requires 13,000. A requires for 1000 it around 50 lakh, and for B it requires 2.5 multiplied by 10 to the power 41. And it is increasing gradually in terms of that complexity. This means that B cannot be used for large input while running algorithm A is still feasible, so that the function growth of the complexity function will be there. The growth of time and space complexity will increasing the input side, and it's suitable measure for the comparison of any different type of algorithm. There are many different criteria to judge an algorithm. There are, first of all, we can say that is it correct? We need to check the correctness. Is it readable? We need to check that it is readable, it is working or not. And third one is how it works, the performance, the way of performing, the way of working of an algorithm. We need to check it out again. A third one and the next line I can say is like performance evaluation can be divided into two major phases. One is performance analysis and in terms of space and time, which are completely machine independent, and that's why I have already rectified and I have already give you the hint. Regarding the space time, the space complexity of an algorithm is the, what is that, the definition of space complexity is very normal, I can say. The amount of time, amount of memory or amount of space required, amount of memory it needs to run for the completion, or I can say the amount of memory required while conversion of input to the output. It means to run the complete algorithm from zero to its output, from source to its output, from starting position to its output is called as the space complexity. Whereas in terms of time complexity, the time complexity of an algorithm is the amount of time, amount of computer time or computation time it needs to run the to run up till the completion. The time complexity of an algorithm is the amount of computer time it needs to run the complete to the completion. We'll see about the space complexity later on, but I can say in brief, related to the space complexity of any algorithm, that is P is given by S of P is equal to C plus SP of I, where C is completely constant. Fixed space requirement in terms of independent the characteristics of an input and output that includes the instruction space, whereas the space of a simple variable that are fixed size structured variable and it may be constant as well. In terms of that pseudocode, which gives you the high level description of an algorithm without the ambiguity, which is completely associated with the plain text, but also without the need to know the syntax of a particular programming language as well. The running time can be estimated in a more general manner by using the pseudocode to represent the algorithm as a set of fundamental operations which can then be I can say like counted. There may be the quite difference between the, yes, that you should be very clear about the difference between the pseudocode and the algorithm. I can brief the difference over here, like variable space requirement in terms of space complexity. An algorithm is a formal definition with some specific characteristics that can be described as a process which could be executed by a Turing that can complete the, you can say like computer machine to perform a specific task. Generally, the word algorithm can be used to describe as a high level task in computer science, as we all know. In terms of pseudocode, I can say it is an informal human readable description of an algorithm that leaving many granular details of it, whereas writing a pseudocode has no restriction of styles, and its only objective is to describe the high level steps of algorithm in a much realistic manner or in a natural language. In terms of this normal examples, I can say like simple arithmetic function or algorithm, say ABC. The pseudocode can be written in terms of written a plus b plus b plus multiplied by c plus a, whatever that thing it may be, plus 4, where the space complexity which is required is of I is equal to 0. Hence, the constant is 0. Hence, s of p is equal to constant. It should not get changed in terms of simple arithmetic function. When we are going to deal with the recursive function of a sum for a sum of list of numbers, where the algorithm sum is equal to list n, and if n is less than or equal to 0, then it can return your function 0 dot 0, else return r sum. That means you can going to sum out the thing, list n minus 1 plus list of n will be there. There are various different methods. I can again explain all these methods to you. One is introduce the variable count into the program, and another one is the tabular method. First is determine the total number of steps. In that, introduce variable count into the program that can determine the total number of steps which are contributed by each statement, whereas steps per execution or frequency, and you can also add up according to the contribution of each and every steps. Second method we can deal with, that is the tabular method, where the statement is already been given, and accordingly you have to rectify the frequency and the number of steps which are required. In that case, you are able to find out the complexity of any algorithm. In terms of that tabular method is quite easy as compared to the variable count program method. Next, the growth of function. How the growth of function occurs in a particular function. In terms of n, if n is nothing but a number of elements required or number of elements present or available, the growth of function is usually described using the big O notation. The growth of function is usually described using the big O notation, where the definition of big O is like simply, let's say f and g be the functions from the integers or the real numbers to the real numbers. We say that f of x is the order of g of x or big O of g of x if and only if there exists a constant c and k such that the mod of f of x is less than or equal to c of mod of g of x. We can say that f of x is the order of g of x. If f of x increases, ultimately g of x will also be increases. Whenever x is greater than k, when we analyze the complexity of the function, when we analyze the growth of the complexity function, say f of x and g of x are always positive. That's why we have mentioned it in terms of mod. Therefore, we can simplify the big O requirement to f of x, which is less than or equal to cg of x, where x is greater than k. K is nothing but again the constant. Uh, for any constant k, I can say, if we want to show that f of x is equal, in the next slide I have explained it in a diagrammatic way, so no need to worry. We can only need to find one pair of constant, that is c comma k, which is never unique. Idea behind Pico notation is to establish the upper boundary. Look, is to establish the upper boundary for the growth of any function, say f of x, for the large value for any different value, say x. The boundary is specified or the limit is specified by the function g of x, that is usually much simpler than the function f of x. We can accept the constant c in the requirement. F of x is less than or equal to cg of x, where whenever x is less than the constant, say k. because C does not grow with X. That's why we are only interested in large X. So if it is okay, then f of x is greater than Cg of x for all x which are greater than or equal to k. Next is the theoretical analysis of algorithm. It is common to estimate their complexity. For example, this particular example in asymptotic sense, that is, estimate the complexity function in an arbitrary large input. The term analysis is very essential and very important part of the computational complexity theory. Uh, why the question arises from last half an hour we are discussing about the same. The question arises why there is a need of analysis. The answer is very simple. The need of for analysis of algorithms and how to choose a better algorithm for a particular problem, as the computational problem can be solved by using different algorithms, as we know that. But by considering any algorithm for a specific problem, we can begin, or we can start the to develop a pattern recognition, so that similar type of problems can be solved by the help of any algorithm. Algorithms are quite often quite different from one another, though the objective of these algorithms are the same. For example, we know that a set of numbers can be sorted using different algorithms. The number of comparisons can perform by any algorithm may vary, and we can say that for same input again it can be vary. Hence, it may not. And in the above slide we have already seen that uh, C does not grow with X. A particular value which does not grow with any different constant. For example, for this particular given example, for x is greater than equal to 1, we have x square plus 2x plus 1 is less than or equal to x square plus 2x square plus x square. And say if x is equal to 1, it may be exactly same in both the cases. Therefore, C is equal to 4 and K is equal to 1. And then we can say that f of x is less than or equal to Cx square whenever x is greater than K. That means that we can say f of x is the order of x square. Accordingly, as if the value of x increases, definitely the value of f of x is also increases. Or I can say, if x cube grows faster than x square, so x3 goes also faster than f of x. Therefore, we always have to find the smallest simple function g of x, for which f of x is order of g of x. Yes. These are the fast list of slowest to fastest growth algorithms, or growth complexities. One is growing as slowest to fastest. Log n is also the one, log n, then n log n. You can see the increment. One is slowest. Log n is next to one. The n is next to log n log n square, n cube, 2 to the power n, and so up and so on up to n factorial, I can say. A problem can be solved by using polynomial. Worst case complexities can be tracked. It can be tractable. Problem of higher complexity are also intractable, and problems that no algorithm can solve are called as unsolvable. You can say that you will find out more about this in the next slides. Now we'll go with that in detail up to about this asymptotic complexity. What happens running time of an algorithm as a function of input size n for large n. What is asymptotic complexity? It is expressed using the highest order term. It is expressed using highest order term of input size in the expression is the exact running time. There are four different cases. Can see analysis is very important. So the main concern of analysis of algorithm is to require the time performance. We perform the following. We perform the analysis by using the four different steps. Majorly three there are. First is worst case. The worst case means that means the maximum number of steps taken for any instance of size A. We can also go with the best case as well. The number of steps of our the minimum number of steps that taken in an any instance for size A, for any size A for a given input, I can say. And average case is nothing but the average number of steps taken for any instance of size A. Next one is amortized. Fourth one is amortized, a sequence of operation that applied to the input size of A averaged over the time, called as amortize. To solve any problem, we need to consider the time as well as the space complexity, as the program that may run on a system where memory is limited but adequate space is available, or maybe I can say vice versa can also be true. In this context, if we are comparing bubble sort and merge sort, both are the sorting algorithm that does not require any additional memory, but merge sort requires some additional space. Though the time complexity of bubble sort is higher as compared to the merge sort, that we need to apply bubble sort for if the program needs to run in an environment where memory is very limited. Instead of running exact time, we can say describes the behavior function in the limit. We are using it by asymptotic notation. Asymptotic notation can be used with the help of a big O, omega, theta, small o, and small omega. We can use it a function over the natural number. Say f of n is equal to order of or omega or theta of n square. That can describe f of n how it grows in comparison to n square. For this asymptotic, we have to define a set of function. In practice we used to need to compare two function size. The notation that describes different rate of growth different rate of growth relations between the defining functions and the defined set of functions can also be possible. In terms of this theta, firstly we'll go with that theta. There are two different constants, C1 and C2. C1 of g of n and C2 of g of n. For the function g of n, we need to define theta of g of n, where big theta, or we can say normal theta, of the function that n as set occurs for the two positive constants, say C1, C2, and n0, such that such that all n are greater than or equal to n0. All n are greater than or equal to n0. We have 0 is less than yes, that matters. C1 is greater than 0. That means all 0, C1 is greater than, is less than or equal to C1 of g of n, which is at the bottom, and in between there is a function which is the function which is greater than C1 of n. C1 of g of n, but the function is less than C2 of g of n. Or in other words, I can say the function is located, or it resides in between C1, in between the two constant, that is C1 of g of n and C2 of g of n. Intuitively, we can say that set of functions that have the same rate of growth of g of n. In other words, I can say that the function f of n is an asymptotically tight bound for the function f of the function g of n is an asymptotically tight bound for the function f of n. Simply like this. There are various examples of this. Now we'll go with the omega. Now we'll go with the big O. For the function g of n, we need to define order of g of n. That is big O of n. Big O of n is equal to the function where all positive constant c and n0 such that the function n is greater than or equal to n0. We have 0 is less than f of n is less than or equal to c of g of n. There is only one constant, that is c of g of n. We can also say that set all the function whose rate of growth is the same as or lower than of g of n, as or lower than of g of n. G of n is an asymptotic upper bound for the function f of n. It directly means that f of n should not go exceed or should not go above g of n. That's why we would say that it's an upper bound for the function f of n. Next is there are various examples related to this. That's positive constant c of n, c and n0, such that all n are greater than or equal to n0. Where we have 0 is less than or equal to f of n is less than or equal to cg of n. In other words, I can also say that the asymptotic behavior of a function f of n that refers to the growth of the function f of n and n gets large. We can There are three different methods related to the recursion method or recurrence. Will not enter in that topic, but I can definitely give you in the brief related to the substitution method, recursion tree method, and third one is the master theorem. In this method we guess that a bound, and using mathematical induction we prove that our assumption was correct in that substitution method. Whereas in recursion tree method, in this method, a recurrence tree is formed where each node represents the cost, and master theorem is nothing but the last option to solve any problem in the world that can in computation. I can say this is another more important technique to find the complexity of recursion function. In that case, any linear function a n plus b is order of n square. How? The answer is very simple. Show that 3n cube is equal to order of n to the power 4 for any appropriate function, say c and n0. The third one, we have already gone with the theta notation, big O notation, and now the third one is the omega notation, where the same, exactly in contrast with big O, this notation may get used. For functions say g of n, we need to define omega of g of n. Big omega of n is set of as the set over there. In that case, big omega of g of n is equal to the function f of n for all positive constants. Yes, of course, we are working only for positive constants c and n0, such that all n are greater than or equal to n0. The condition is very same. We have 0 which is less than or equal to c g of n, and which is less than or equal to the function say f of n. We need to set all the functions whose rate of growth are same or as higher than that of g of n. It means the function f of n or the g of n is an asymptotic, the constant g of n or the function g of n is an asymptotic lower bound for the function f of n. It directly means that f of n should not go downward than g of n for all n who are greater than or equal to n0. It means it should be any positive value. In other words, I can say that g of n is an asymptotic lower bound for the function f of n. Example, in that case, this positive constant c and n0, such that all n belongs to all n those who are greater than or equal to n0, we have 0 which is less than or equal to cgn, and which is less than or equal to the main function say f of n. Square root of n is equal to omega of log n. We can choose any value say c and n0. In the relate there is a big relation between these two, between these three, theta omega theta big O and omega respectively over here. I can see in the diagram, I can explain with the help of this diagram. The function f of n is the tight bound in between the two constants c1 of g of n and c2 of g of n. In big O, I can say g of n is the upper bound for the function f of n, because whenever f of n grows, g of n also grows, but g of n sorry the but the function f of n does not go above g of n. In omega, it is in complete contrast. I can say the constant say g of or the c g of n, that is the constant g of n, is the asymptotic lower bound for the function f of n. or f of n is equal to omega of g of n in omega, and in big O, f of n is equal to order of g of n. According to the g of n, it may work. And in terms of theta, we can say that f of n that is equal to the theta of g of n. Theta of g of n, it directly means that it's the constant, is the constant between the function f of n. Next is relationship between theta, omega, and for any functions like g of n, f of n is equal to O only. F of n is equal to omega order of g of n, and f of n is equal to omega of g of n. That is, in practice, asymptotically tight bounds are obtained from asymptotic upper bound and lower bound, as we know. And then the running time complexity or running times are as follows. So in terms of that worst case running time, order of f of n bound on the running time of every input, omega sorry theta f of n bound is the worst case running time, and theta f of n bound on the running time of every input. Accordingly, we can say that certain example with the help of, say, it can be applicable in terms of insertion sort, in terms of any different sorting technique. In the worst case, so sorting as a problem is order of n square, and it may be, the answer is very simple. Any sort algorithm must look at each item. So sorting is omega of n, and merge sorting is like theta of n log n. In the worst case, later we will prove that we cannot hope that any comparison sort to do better in the worst case. Lastly, asymptotic notation in equation is like this asymptotic function, and these small notations are again be the properties of that thing. Lastly, we'll go with the second part of our today's class, where we can go with the summary and the summation various along with the various algorithms like this. We need to do the summation formulas, like for computing the running time or of iterative constructs loops, that's CLRS, that may be there. Accordingly, the maximum subvector which is given as an array, say for example 1 to n for any numeric value, and it can be positive, 0, or any negative value. Determine it can also be determined the subvector for all the functions a, I to j, and 1 is less than or equal to I is less than equal to j is less than equal to n, whose sum of elements is maximum over the subvectors. In terms of that, in terms of that next way of working of a particular algorithm, the designing of algorithm, complexity analysis, and algorithm is a very essential part. In that case, the space complexity and asymptotic notation, where execution time on the algorithm depends on the instruction set, whereas the execution time are completely depends on the instruction set. The number of instruction set which we are given to the particular algorithm can be exit and can be work it out accordingly. In terms of processor speed, disk input output speed, etc. Hence, we estimate the efficiency of an algorithm by asymptotic manner. The time function of an algorithm is represented by using, say, t of n, where n is the input size, and different types of asymptotic notations are used to represent, that we have already discussed, used to represent the complexity of an algorithm. It may be in it, as we have already discussed it about big O, omega, theta, little o, and little omega. Next is in other words, I can completely say in terms of big O, it is the it is the most commonly used notation, as a function f of n can be represented in order to g of n, and that can be that is order of g of n if there exists a value of a positive integer n as n0 and a positive constant c, such that f of n is less than c of g of n for n is greater than n0 in all cases. Next, in the cubic series for n is greater than equal to 0, I can say this particular series summation I or the limit I is equal to 1 to n up to I3. I to the power 3 which is equal to I to which is equal to 1 to the power 3 plus 2 to the power 3 and so on up to n to the power 3, whatever the number of variables are there, and it's equal, ultimately it equals to n square, n plus 1 whole square upon 4. That is the cubic series. In terms of geometric series, for real x is not equal to 1, in that case the value k is equal to 0 to n, x to the power k is equal to 1 plus x square up to x to the power n, which is, at last we can summarize it in this manner, is equal to x to the power n plus 1 whole minus 1 upon x minus 1. The telescoping series and differentiating series are not that much in use, and one with the help of another example I can say it, the divide and conquer strategy. This is the designing technique. There are four different designing techniques. One is divide and conquer, another one is dynamic, another one is greedy, and and uh, graphical methods as well. So we'll go with first divide and conquer method, or divide and conquer algorithm first. How it works for a algorithm. The most well-known algorithm, it is a most well-known algorithm design strategy where divide instant that it can explain it in this with these three different points. First is it can divide the instance of a problem into two or more smaller instances. It can solve smaller instances recursively again, as if in terms of binary we have just now discussed it in this video itself, where uh, firstly, the whole list of elements can be divided into two different parts, unless and until we can subdivide it into, until and unless we'll get the final out, we'll get our search algorithm for which we are searching for. In divide and conquer approach, the sub problems is divided into smaller sub problems, and then the sub problems is solved independently. It is used to it can be able to obtain the solution to original instance by combining this solution again. After dividing, we need to again break it down. For example, this is the diagrammatic representation of the same. A problem of size n can be divided into sub problem of size n by 2 on the left hand side and on the right hand side, and the sub problem 1 of size n by 2 can again be divided into until the solution of a sub problem 1, until we get the solution of the sub problem 1. Same thing, we have to do it on we have to do I mean we have to perform it on the right hand side. This When we keep on dividing the sub problems into smaller sub problems, we may eventually reach at the stage when where there is no more further divisions. In that case, those atomic smallest possible sub problems are solved. The solution of all sub problems is finally merged in order to obtain the solution of an original problem. In that case, then and only then we are then merging it together to get to get a solution to the original problem, or for finding the solution to the original problem. There are various examples of this divide and conquer strategy, where divide and conquer algorithm. I can say like sorting, merge sort, and selection sort are the best example of divide and conquer strategy or divide and conquer algorithm. In terms of tree, binary tree traversal based on divide and conquer strategy. Multiplication of large integers can again be based on this divide and conquer. Matrix multiplication, that is Strasson's matrix multiplication algorithm is there, which is completely based on divide and conquer strategy. Closest pair and convex hull algorithm is also there. And lastly, the binary search that we have already discussed in this today's session is again belongs to this divide and conquer strategy. Generally, divide and conquer recurrence is also been there, which we are using it by applying the master theorem. For example, say t of n is equal to a t n by b plus the function f of n, where the function f of n is a subset such that or the sorry it is a theta of n to the power d, where d is greater than or equal to 0 in integer. Where the master theorem, three different cases, if a is less than or equal to, if a is less than b to the power d, the function t of n is such that theta of n to the power d. If a is equal to b to the power d, t of n is equal to T of n is such that theta of n to the power d log n. And third case, if a is greater than b to the power d, in that case T of n is such that so theta of n to the power log a to the base b. The results, the same results hold with omega instead of the same results hold with big O instead of theta as well. We can give you the we can also solve it with the help of the replacing by replacing the values with any integer. In that case, if we are going to deal with the merge sort, we can split the array a 0 to n minus 1 into about equal halves or exact equal halves. That means the sub problem on the left hand side and on the right hand side from the center, and again make copies of each half into the arrays b, c, d, and so on. Sort the arrays b and c recursively. Merge the arrays b and c into the array a as follows. Firstly, we'll do the repeat the process until and unless no elements remain in one of the arrays, and we can able to compare the first element with the remaining unprocessed portions of the arrays which are not yet subdivided. Second point we can discuss it about in terms of merge sort. We can copy the smaller it into a while incrementing the index indicating the unprocessed portion of that array as well. Nextly, once all the elements in uh, once all the elements in one of the arrays are processed, copy the remaining unprocessed element from the other array into A. So the algorithm or the pseudocode for the same is as follows: sort arrays A 0 to n minus 1 by recursive merge sort. Input an array A 0 to n minus 1 for order elements, and output array is for A 0 to n minus 1 sorted in non-decreasing order. That non-decreasing order is very important. This is the normal pseudocode for merge, where merge two sorted arrays into one sorted array, and it may be input of arrays B 0 to p minus 1 and c 0 to say q minus 1, that both are very sorted, and accordingly I is less than p and j is less than q, so that if b of I is less than or equal to c of j, the condition ak tends to b of I, and I is equal to I plus 1, whereas j, if it is in terms of j is also equal to j of j plus 1. Next is this merge sort. This is a normal diagrammatic representation of merge sort algorithm, where the given list of elements like 8, 2, 3, 9, 7, 1, 5, and 4 is given to you. We need to divide the whole list of elements into two different parts. One is on the left hand side and another one is on the right hand side. 8, 3, 2, and 9 is the first part. 7, 1, 5, 4 is the second part. Again, the list of these four elements can again subdivided into two different parts. Unless we need to divide it in divided this list of elements unless there is no further division is possible. The no further division is possible only and only when we have only one element remaining with us. So the 4 can be divided into two different parts again, two different parts, that is of the element of the size 2, 8 and 3, 2 and 9, 7 and 1, and 5 and 4. Again it can be subdivided into 8, 3, 2, 9 for a single elements, and then we need to merge it out by according to the ascending order. According to the ascending order, I can say 8 and 3. When we are comparing 8 and 3, the 3 is smaller than 8, so we need to keep 3 first and then 8. Same thing, 2 and 9, 2 first, 9 then, 7 1, 1 7, 5 4, 4 and 5, like this. So again that two parts can again be merged again together: 2 3 8 and 9, 1 4 5 and 7. And this whole list of four elements can again be merged together for getting a complete ascending order in such a manner that in a sequence like 1 2 3 4 5 7 8 9, like this. This is the normal analysis of this merge sort. How that merge sort works, I have explained it with the help of that diagram, with the help of that pictorial representation. This quick sort again with that belongs to your divide and conquer strategy, but there is one different way. We have to firstly find out the select a pivot element. It is a partitioning element where we can compare it with that particular pivot element or pivot value, whatever that pivot value, what that may be anything, that may be any different value from the list of elements. We need to compare the remaining values with that pivot, and whatever the values which are less than pivot will be on the left hand side, and whatever the values which are on the right which are greater than the pivot are be on the right hand side, if you are sorting all the elements in ascending order. Lastly, we'll say that the quick sort example is like this: 5319824 7, and we can simply sort it by using this particular algorithm or this particular steps. There are three different cases of this quick sort algorithm and a time complexity related to analysis. The best case is theta of n log n. In terms of worst case, in terms of worst case analysis of quick sort, the time complexity is theta of n square, and average case in random access it is theta of n log n. Improvements in it is in terms of better pivot selection, that may be median of three partitioning, switch to insertion sort for any small sub files, and elimination of recursion can also be there in terms of this while we are combining it to 20-25% improvement. Consider the method for choose for method of choice for internal sorting of larger files or large files which are greater than n, which is n is greater than or equal to say 10,000 or any different greater value. Binary tree algorithm can also be there as a part of classic traversal. In terms of when we are looking into the matter in the third lecture after this, we'll see these trees in detail over there. The complexity and the tree traversing techniques like in order, say pre-order and post-order, this same algorithm is used. In order, where the root is visited in between the left and right subtree. Pre-order says that root should be visited first, then left, and then right subtree. Post order, I can say firstly we'll visit the left side, then the right, and at last the root. Ultimately, the efficiency is theta of n. In terms of this binary tree algorithm, when we are entering in the tree, we'll see it in detail. While the computing the height of a binary tree can be calculated with the efficiency of theta of n as well. Multiplication of large integers can also be possible with respect to this particular algorithm. We can use it. For example, a is having a particular value and b is having again a very large value. The grade school algorithm is applicable in terms of that large integers, where the efficiency is n to the power 2 one digit multiplication. It can be applicable with the help of only one digit. Divide and conquer, we are very much familiar right now, where the small example of a multiplied by b, where a is equal to say 2135 and b is equal to say 4014. In that case, a is equal to 21.10 to the power 2 plus 35, and b is 40. As if we are taking it in terms of integer first, 40.10 to the power 2, since it is having the 1000, so 10 to the power 2 is nothing but 100 plus 14. Accordingly, we can multiply all the things and we'll definitely get the answer in terms of mn is equal to 4m of n by 2, where m of 1 is equal to 1. uh, we can able to find out the answer. We can able to find out the solution: 3 to the power log 2 log 2 to the power n, where where n log 2 to the power 3 is equal to n to the power 1.585 if we are calculating it. In that case, we can definitely multiply with the with this particular normal value 2135 multiplied by 4104. So next matrix multiplication is like Strasson's matrix multiplication algorithm, where we can able to multiply the two values by using the matrices. We are using various formulas. There are 7 different formulas for matrix multiplication algorithm. You can choose any of the one to go with that Strasson's matrix multiplication algorithm. If n is not the power of two matrices can be padded with zeros, and the number of multiplication m of n is equal to 7m of n by 2 plus comma m, where m of 1 is equal to 1, and solution m of n is equal to 7 to the power log 2 to the base n, sorry, log 2 to the power n, which is somewhat equivalent to n to the power log 2 to the power 7, and log n 2 point n to the power 2.807 versus n to the power 3 of brute force algorithm. That brute force algorithm is the algorithm which is better asymptotic efficiency are known, but they are even more complex than each other. Next is there are this closest pair algorithm and this quick hull algorithm. Basically, quick hull algorithm is not that much essential in terms of our algorithm and in terms of our gates perspective. Smallest convex set that includes given points. We can assume the points by sorted x coordinate values, and we can identify extreme by points p1 and p2, which are leftmost and rightmost. In that case, where we can compute the upper hull recursively. So ultimately, if we are computing the lower hull and the upper hull separately, this whole algorithm can be exactly working as a quick hull algorithm. The worst case time complexity for quick sort by using quick hull algorithm is order theta of n square, and average case it is theta of n. This is all about the today's class. I hope my deliberation is very clear to you. Over to you, Neeraj sir.
Yes, sir. Thank you so much. Hello.
Okay, yes sir.
Okay, sir. Thank you so much.
Thank you.